One to one. Buenas tardes.
Buenas tardes.
Good afternoon, everybody. We continue with our course, and today we are touching a little bit cross-field with biology. So we will discuss a little bit of biological effects of ionizing radiation, as they are understandable by physicists. So we will cover cellular effects of radiation and effects of radiation in humans. So, first of all, for more than 100 years, interest in the nature of the biological actions of ionizing radiation has been fueled by the so-called radiological paradox. Professor Dole already discussed this from the point of view of biologists. So we have to rearrange this a little bit to understand better. So its essence lies in the fact that the transfer of sanity energy in the human body by radiation can lead to a catastrophic consequence. Imagine that the body of a person with a mass of 100 kilograms was transferred to a thermal energy equal to 1000 joules. From the point of view of molecular physics, the consequences of such an impact are simply negligible. It will lead to a short-term increase of human body temperature by no more than 0.002 of a degree. If the same energy is transferred to the human body by gamma radiation, then the consequences will be tragic or fatal. Such exposure is characterized by an average absorbed dose over the body equal to 10 grays. If you divide 1000 joules to 100 kilograms. The tragic experience of radiation accidents shows that such exposure is a high probability leads to the death of the person in 10, maybe 20 days. The thermal energy transferred to the human body is distributed evenly and in arbitrary small portions among all molecules of the substance. Therefore, in the case considered above, the energy transferred to each molecule is so small that its effect is not capable of destroying a single molecule. The energy of ionizing radiation is not transferred to all the molecules of a substance, but only to a small part of them during the interaction of charged particles with atoms and molecules. The transfer of energy leads to significant changes in individual molecules, their ionization or excitation, which can destroy the molecules. The impact of ionizing radiation on living objects causes a significant change in the properties of biological macromolecules that are important for the existence of cells. In spite of the relatively small number of such primary designs, they are sufficient to produce a visible biological effect. Human tissues are made up of cells that are grouped into body organs and systems to perform specialized functions, such as skin cells and blood cells. While the cells of various organs vary in size, shape, and detailed structure, some features are common. Each cell is characterized by a membrane enclosing gel-like cytoplasm composed of 85% from water. Chemicals and structures such as the nucleus, organelles, and chromosomes containing DNA, marked by F in the picture. The role of damage to the cell nucleus in the biological action of ionizing radiation was revealed almost 100 years ago. As a result of an intensive experimental studies of the biological effect of ionizing radiation. Already in 1903, it was established that the main role in the radio sensitivity of a cell is played by damage of its nucleus. And a year later, in 1904, a fundamental law was formulated. The sensitivity of cells to the effect of ionizing radiation, or biological, the action of X-rays. Is stronger the higher the reproductive activity of cells, and the lower the degree of cell differentiation in accordance with its morphology and function. By the name of the authors, French radiobiologists, this law is called the rule of Bergonier and Tribondot. The result of the generalization of radiobiological data was the emergence in 1922 of the first theory explaining the biological effect of ionizing radiation, cell death under the action of radiation, by the appearance of ionization events in the sensitive volume of the cell. The theory of point heat by Isauer. 3 years later, in 1925, the works of Madsen, Filipov, and Müller proved the mutagenic effect of ionizing radiation. The study of the structure of cell nucleus and the discovery of their material carrier of cellular heredity, desoxyribonucleic acid, DNA, made it possible to create a more or less definite picture of the biological effect of ionizing radiation. The double helix of DNA is the most important macromolecule of the cell. The further phase of the cell depends on its integrity. The information involved in DNA is necessary for cell reproduction, its division, and therefore for maintaining the integrity and function of biological tissue. The energy of ionizing radiation passing through biological tissue is transferred to atoms and molecules. This leads to the formation of ions and excited molecules. The primary radiation chemical charges in molecules are based in two mechanisms: ionization and excitation of atoms and molecules, its direct effect of radiation, and transfer of energy to other atoms and molecules of the cell. This is going through the indirect effect of radiation. Consider the mechanism of energy transfer to water molecules, of which 70–80% of the human body consist. During the passage of gamma radiation, as a result of the interaction of radiation with matter, due to the absorption of energy, a water molecule is ionized, as a result of which the molecule loses an electron, which also quickly transfers its energy to the surrounding water molecules. As a result of this, radical ions are formed. Free radicals contain unpaired electrons, and are extremely reactive. The lifetime of the radical doesn't exceed 10 microseconds. During this time, they either recombine with each other or react with substances dissolved in water. In the presence of oxygen dissolved in water, other radiolysis products are also formed. A free radical of hydroperoxide, hydrogen peroxide, and atomic oxygen. These chemically active products, together with the direct ionization of molecules and the breaking of interatomic bonds, have a direct damaging effect on the totality of vital molecules, and first of all on DNA. Ionizing radiation, like other factors, physical and chemical, can lead to the destruction of individual chemical bonds in DNA, to the breaking of one or both of its strands. If one strand is damaged, then it is possible to restore the DNA structure due to the action of repair mechanisms, which using the second strand complementary to the damaged one, and are able to completely restore the damage to the first. In the range of low doses, the occurrence of single DNA breaks is typical when exposed to radiation with a low LET, as photons, electrons, fast protons. If both complementary DNA regions are damaged, then such repair becomes impossible, and this leads to unrepairable DNA damage, which can have serious consequences for the fate of the cell. Such breaks, as a rule, lead to inactivation and cell death. In the region of low doses, the occurrence of double DNA breaks occurs when exposed to radiation with a high LET, alpha radicals, slow protons. In this case, it is enough for the track of one heavy charged particle to cross both strands of DNA and damage them. In this region of high doses, the occurrence of double DNA breaks is also possible under the influence of radiation with a low LET. For such an event, it is necessary that the tracks of two charged particles, for example, electrons, cross the complementary sections of the DNA and damage them. The functioning of the DNA damage repair system is of the almost is of the utmost importance in the fate of the irradiated cell, together with the primary effect, DNA damage. The fate determines the early cellular response to radiation exposure. This proper repair, usually such repair is possible only for a single DNA breaks. No effect of irradiation are observed. On the contrary, erroneous repair of single break can lead either to cell death or to the appearance of its viable descendants and their death or cell inactivation. Maybe it's reproductive death. Or to the appearance of viable descendants with new properties, mutant cells, during cell division. Radiobiological studies have shown that in the region of low doses, the same radiobiological effects of radiation accordance can have the same degree of severity S, and at different doses D. Here, doses D, and here severity S. And as you see, it's different type of radiation, alpha particles, neutrons, and gamma. Take into account these differences. The concept of relative biological efficiency of radiation was introduced, and its dependence on a variety of characteristics of radiation, including its LEP, was studied. The relative biological efficiency, effectiveness of some radiation is taken in equal to the ratio of the absorbed dose dx here. So different type of particles of quantas to the so-called dx of the exemplary reduction that causes a certain biological effect to the absorbed dose dx of its radiation that causes the same effect. So X-ray radiation with a limiting energy of 200 kiloelectron volts is taken as exemplary, as tested. Numerous studies have shown that when the same biological objects are irradiated, the RBE of radiation depends on the specific effects, radiation conditions, type of radiation, its energy and intensity. The RBE depends on the LET of ionizing particles and is approximately the same for different types of radiation and is equal LET. The relative biological effectiveness or RBE of radiation depends on its LET. With an increase of LET radiation, the probability of cell damage increases, and its ability to restore the damage decreases. A noticeable increase in RBE begins at a LET of about 10, starting from 10, and reaching its maximum to about 100 kiloelectron volts per micrometer. And then drops rapidly. This dependence is in agreement with the idea that a cell dies after absorbing a sufficient amount of energy in a certain critical volume of its nucleus. This probability gradually increases with increasing LET. Upon reaching a certain radiation energy transfer density or its LET, the association occurs when each subsequent particle loses its energy already in the destroyed cell. In this case, the efficiency of exposure to radiation having such a sufficiently high LET drops sharply because energy is wasted. According to the modern concepts, the biological effects of radiation are divided into deterministic and stochastic. The main target for radiation is the cell nucleus, The cells that make up human organs and tissues are different, but two large groups can be distinguished among them. The first includes male and female germ cells, as a result of the fusion of which a human embryo may arise. The second group, the group of somatic cells, includes all other cells of the human body. Development of deterministic effects is based on the death of somatic cells, cells of organs and tissues, under the influence of high doses of radiation. The development of stochastic effects is based on the charge and on the change in the nature of cells under the influence of radiation. At low doses, irradiated cells, also damaged by radiation, survive and acquire new qualities that are based on their descendants. Such cells are called mutant cells. Deterministic effects of radiation occur when exposed to high doses. These effects include diseases that never occurs in unexposed people. Acute and chronic radiation sickness that occurs during general radiation of the human body. Local damage to organs and tissues, for example, radiation burns like this. Radiation cataract, which occurs when the lens of the eye is irradiated. Anomalies and congestional malfunctions of newborns, which are deterministic effects of irradiation of the fetus in the embryonic period of development. The basis for this effect, first of all, is the damage to a significant proportion of the cells of the irradiated organ. Diseases that are attributed to the deterministic effects of radiation do not occur under the influence of other physical or chemical factors. The relationship between such an effect and exposure to radiation is direct or determined or deterministic. The dose response relationship for deterministic effects has a dose threshold. Under irradiation, under irradiation with a dose below the threshold effect, no effect develops, and above it, the severity of the effect depends on the dose. The more cells that make up the tissue are damaged, the more its integrity and function are violated, and the more severe the course of the disease, and the more serious its consequences can be. An increase in the dose is accompanied by an increase in the proportion of damaged origin cells, as a result of which the deterministic effects become more pronounced and occur sooner. The value of the threshold dose is determined by the radiosensitivity of the cells of the irradiated organ and the body's ability to compensate or restore such damage. It depends on the rate at which the organ is irradiated. It is on the radiation dose rate. The lower the dose rate, the more time is needed to form a dose and to restore damaged cells and tissues. And the larger the dose is necessary for the development of a deterministic effect. In accordance with the rule of Bergadier and Tripandot, the threshold dose is the smallest for rapidly renewing tissues, such as red bone marrow, and the largest for slowly renewing cellular systems, such as the nervous system. According to this pattern, the radiosensitivity of a person increases with a decrease of his age. The human fetus has the highest radio sensitivity, and the adult person has the least sensitivity. The same issue of different people differ in radio sensitivity. The set of people characterizes the probability with which in this group there are people with one or another value of the threshold dose. The slide shows the probability of developing certain deterministic effects in human adults, in healthy adults, as a function of external exposure dose. The main pattern of development of several deterministic effects of radiation are as follows. Due to the variability of individual radiosensitivity of people, any effect is characterized by a range of threshold doses. Different tissues of even one organ differ in radiosensitivity. Therefore, with an increase in the radiation dose, the biological effect may change, the occurrence of which ultimately leads to the serious illness or death. With an increase in the radiation dose, the severity of the effect increases, which is reflected by the reduction in survival time, the time interval between exposure and death. The decrease in the dose rate and an increase in the duration of irradiation and time, the risk of developing a deterministic effect decreases due to the restoration of the functions of the affected organs. In severe deterministic effects, as a rule, arise during radiation accidents. Thus, for 50 years, from 1950 to 2000, in the leading clinic of radiation injuries of the former Soviet Union and now Russia, in the clinical department of the Institute of Biophysics, 321 patients diagnosed with acute radiation sickness were treated, of which 69 people could not be saved. According to the World Health Organization and the International Atomic Energy Agency, in industrialized countries, due to violation of technology, equipment malfunction, or personal errors, there can be up to 10-12 cases of increased or accidental exposure from various sources of ionizing radiation per year, of which 1 or 2 cases may develop radiation exposures, illness, or other severe deterministic effects of radiation. As a result of the accident at the Chernobyl nuclear power plant, as seen in the slide, acute radiation sickness was observed in 134 people, firefighters and NPT personnel, of which 28 people died in 1986 from combined external gamma radiation and contact skin exposure. 17 people died in next 20 years from various causes not directly related to radiation. There were no cases of acute radiation sickness among the population. Development of stochastic effects of radiation has been the subject of radiobiological research for more than 100 years. Experiments have shown the possibility of developing radiogenic caused by exposure to radiation cancers and dietary diseases in irradiated animals. The main source of data on the development of these diseases in humans are long-term studies of the consequences of the atomic bombing by the American Army of two Japanese cities, Hiroshima and Nagasaki, in August 1945. To date, the results have been obtained from a study of the effects of exposure to more than 200,000 atomic bomb survivors and their descendants. Studies have shown that under the influence of sufficiently large doses of radiation, more than 0.2 grays, when the whole body is irradiated with photons, radiogenic cancers develop in some exposed doses. The whole body is irradiated with photons. Radiogenic cancers develop in some exposed people. Radiogenic hereditary diseases have not yet been found in individuals from this group. The development of this kind of disease has been proven in other studies of large groups of exposed people has not been proved. Until now, the most common view on the mechanism of development of malignant neoplasm of cancer during irradiation is the idea of mutations in somatic cells caused by exposure to ionized radiation. A mutation is a natural or artificially induced persistent change in cells structures responsible for storing hereditary information. These structures ensure the transfer of hereditary information from cells in the process of division, without which the existence of the organism is impossible. As a result of such mutation, a cell arises with properties that are not characteristic of a given tissue, for example, capable of uncontrolled division. It is from such cells that rampantly growing malignant or cancerous tumors consists. It is believed that a single affected cell, the carrier of somatic mutation, can give rise to the development of cancer. As a rule, it takes years after exposure before the exposed person develops radiogenic cancer. All this time, the development of the tumor does not reveal itself. This period of latent development is called the latent period. Its value is different for different tumors. The minimum duration of the latent period for the development of radiogenic cancer in humans is 10 years for malignant tumors and 5 years for leukemia. According to modern ideas about the patterns of the appearance of malignant tumors, irradiation doesn't lead to the formation of cancers of a specific type. The appearance of cellular mutations is a fundamental phenomenon underlying the development of living organisms. Thanks to him, microorganisms adapt to the action of antibiotics, and children turn out to be an inexact copy of their parents, slightly different. Cancers are fairly common cause of death in people. On average, 20 to 30% of people in developed countries die from cancer. Exposure to radiation leads to an increase in the frequency of mutations and to the appearance in the irradiated population of additional tumors and leukemias. which in their development are no different from ordinary spontaneous cancers. The most important feature of radiation carcinogenesis is probabilistic nature of the manifestation of this effect. It is possible to predict the expected number of additional cancers, tumors, or leukemias in such a group, but it is impossible to specify who exactly will develop cancer caused by ionizing radiation. This means that by analyzing the effects of exposure to radiation on the large group of people exposed to the same dose under certain conditions, it is possible to establish a probabilistic relationship between the radiation dose and the increase in the number of cancers due to exposure. However, it is not possible to determine which disease is a consequence of exposure and which arose spontaneously. A study of the consequences of the atomic bombing showed that the increase in the incidence of cancer in a group of equally exposed people at doses of more than 0.2 grays is proportional to the radiation dose. There are no reliable data on this dependence at lower doses. Different hypotheses for the development of radiogenic cancer lead to different dependencies, as shown on the slide. So this low dosage area is like unknown terra incognita. Analysis of the stochastic effects of ionizing radiation in Japanese cohorts was extremely important for the development of radiation safety. The unfolded probability of death from radiogenic cancers for the Japanese cohort is presented on this slide. For different age cohorts with different doses of radiation, one should expect other absolute levels of manifestation of effects with similar dynamics, which is characterized by two waves. The first, we measure death from leukemia, and the second from solid cancers. The study of radiogenic stochastic effects during irradiation with high doses showed that the probability of their occurrence is proportional to the dose. The severity of the manifestation does not depend on the dose, and the development of cancer is characterized by a significant time of latent development or latent period. Evidence of the occurrence of cancer under the influence of low doses of radiation has not been found. Accordingly, the dose dependence of the risk of developing cancer under the action of low dose radiation is also unknown. Such an effect occurs in nature. With the development of radiation safety, the need to have such a dependence became obvious, and in 1977, the ICRP proposed, ICRP is International Committee on Radiation Protection, proposed to accept such a dependence based on common sense. According to the ICRP, in the field of low doses, the dose-response relationship is a simple proportionality between dose and risk, based on the linear no-threshold or non-threshold hypothesis, abbreviated as LVH. Linear non-threshold hypothesis, or of the development of stochastic radiation effects. This hypothesis was first formulated in paragraph 27 of the recommendations by ICRP from 1977. It says the relationship between the dose received by an individual and any biological effect caused by radiation is very complex and requires further study. For the purposes of radiation protection, some assumptions must be made. One of the main assumptions is that for stochastic effects, a linear non-threshold relationship between the dose and the probability of the occurrence of the effects under normal irradiation conditions is accepted. So they just accepted the theory of non-threshold radiation. So the linear non-threshold hypothesis of the development of radiogenic stochastic effects postulates that these effects can occur at any level of exposure with probability proportional to the dose. Thus, also evidence of the development of additional cancers at low doses was not found. It was assumed that the increase in the frequency of development of stochastic effects in a group of equally exposed people is proportional to any dose of radiation received by them in excess of the usual background radiation. And illustration of this dependence is a figure on the slide. It shows the total cancer mortality as a function of the dose of uniform irradiation of the whole body with photons. Thus, stochastic effects are recognized as non-threshold, and consequently, there are no radiation doses at which the probability of their development can be taken equal to 0. This assumption leads to an extremely overestimated risk of exposure to low doses of ionizing radiation. The decision taken is entirely due to the desire to simplify methods for assessing low doses of radiation, and at the same time, at which the development of radiation effects has not been proven. For the purpose of radiation protection and safety, radiation effects are considered, the development of which can lead to premature death or a significant reduction in the period of normal life. Deterministic radiation effects, for which the relationship between the radiation dose and the development of the effect is more or less unambiguous, is deterministic. This first group. The second is stochastic effects of radiation, for which such a relationship is of probabilistic or stochastic nature. The category of stochastic effects includes cancer and inherited diseases, like genetic effects. The radiation causes an increase in the likelihood of such diseases that spontaneously occur without any exposure and are observed with varying frequency in large group of people. At the same time, radiogenic diseases are indistinguishable from spontaneous ones, which makes it extremely difficult to determine the relationship between the developed disease and the exposure. It is recognized that modern methods make it possible to establish the manifestation of radiogenic cancers only for doses of uniform irradiation with photons of the whole body of more than 200 milligrays per year. The probability of developing stochastic, blue curve on this slide, and deterministic effects shown by thin red curve on this slide. The radiation increases with increasing dose. This leads to competition between deterministic and stochastic effects of radiation as causes of premature death in exposed people. Shown by thick red curve on this slide. At low doses, the probability of premature death is small, and its value is determined by the probability of developing stochastic effects. As the dose increases, the probability of cell death increases faster than the probability of their mutation. So the main effect leading to premature death of people with high doses is a deterministic effect of radiation. In this way, with external irradiation of the whole body with photons with a dose of less than 1 gray, the main cause of premature death is radiogenic cancers, and with irradiation with a dose more than 4 gray, deterministic effects of radiation. When irradiating the whole body with a dose of from 1 to 4 grays, premature death can be associated with the development of both deterministic and stochastic effects of radiation. A causal relationship between cancer death and exposure cannot be established if the whole body dose does not exceed 0.1 gray. In this dose range, the linear non-threshold hypothesis is adopted. So, this lecture is finished for this. Any questions, please?
I have a question. As I could understand, there is not much information about the consequences of low doses. But in the current time, are there more evidences about it? About what are the consequences?
As I understand, all information is accumulated by International Atomic Energy Agency and Special Committee, ICRP. And every year they publish the special reports in which, according to which we are having our decisions. So we've taken this approach or reduced and rejected it. At least now we are taking still that at the low doses. We are working with as previous stages. Nothing is changing rapidly in this area. It's very conservative science. Okay, many online means. Thank you very much.
Thank you.
About your